So today we're going to start talking about solving trigonometric equations. And we're going to start with a minimalist unit circle. So we remember that whenever we have a 30-degree angle, we multiply by pi over 180, we get a pi over 6. Any 45 is a pi over 4, any 60 is a pi over 3, and any 90-degree angle is a pi over 2, 9270. So when you are working with the bare minimum that you have to draw is in x and y axes, and then 3 dots in the first quadrant, 3 in the second, and so on, and you can count your way around the circle. I just added color to help remember which ones are where. So we're going to solve 1 minus 2 cosine of x equals 0 and find all the possible solutions for this equation. So if we start with 1 minus 2 times the cosine of x equals 0, and we're trying to get that x all by itself, the first thing we need to do is remove the 1 from both sides, and we'll have a negative 2 cosine of x is equal to a negative 1. And then we unwind the equation again a little bit more. We divide by negative 2, and the cosine of x is equal to a positive 1/2. Then we ask ourselves, well, how do we get to that x if there's a cosine of x? So we need the inverse of cosine, and it's not a trick question. We actually want to find the inverse cosine of the cosine of x, because an inverse of a function eliminates it, and we have simply x. But whatever we do to the left side, we have to do also to the right side, so we need to take the inverse cosine of 1/2. So remember that table of 9 that I keep telling you have to know, forward, backward, inside out. This is the cosine portion of the table of 9, and we're looking at the 30, the 45, and the 60, the pi over 6, pi over 4, pi over 3, and we know that the cosine of 60 is 1/2. So this is the number we're looking for. That means that we're looking for pi over 3 or 60 degrees. So x is going to be a pi over 3. It's easier to write these in radians. But that's only half of the answer, actually even a smaller portion of the answer than half, because we're asking ourselves, where else is cosine going to be positive? Well, it is positive in the first quadrant and also in the fourth quadrant. So we want this pi over 3, but we also want a pi over 3 in the fourth quadrant. And if we count by our pi over 3's, 1, 2, 3 pi over 3, 4 pi over 3, 5 pi over 3, we have another possible solution. But then we have to ask ourselves, are these all of the solutions? And we know that cosine is negative in the second and the third quadrant, but we also know that we're not restricted in general to just one rotation around the unit circle. Excuse me. So if we added 2 pi to our solution, we'd have another one. And if we added another 2 pi to our solution, we would have another one, and another 2 pi, and so on. So we need not just 2 pi, but 2 pi n, where n is an integer. Now we have all of the possible solutions without having to write an infinite number of solutions and be here all day. So here's our second equation, and it's asking us to solve the sine of x plus 1 is equal to a negative sine of x. So if this had been x plus 1 equals negative x, we would simply add x to both sides. So let's add the sine of x to both sides. And we will have 2 times the sine of x. 1 sine of x plus 1 sine of x equals 2 sine of x. And we need to subtract the 1 from both sides, so we get 2 sine of x is equal to a negative 1. When we divide by 2, the sine of x is a negative 1/2. So we have to eliminate the sine. The inverse of sine is inverse sine. That gets us x on our left side. Whatever we do to the left of the equation, we have to do to the right side of the equation. So we ask ourselves, in our table of 9, specifically the sines row of our table of 9, where is the sine going to be a positive 1/2? And that occurs at 30 degrees or pi over 6. So we know that we want a 30-degree angle, a pi over 6 radian measure, in the 2 quadrants where the sine is negative. In these 2 quadrants, the sine is positive, so we want a pi over 6 angle in the 3rd quadrant and a pi over 6 angle in the 4th quadrant. So if we were at 6 pi over 6 when we were at pi, we'll be at 7 pi over 6 in the 3rd quadrant and 11 pi over 6 in the 4th quadrant. Because we need to include all solutions, we also need to say any rotation about this unit circle will also do the trick. So we add our 2 pi n's and we're finished. In our next example, we're solving the tangent squared of x minus 3 equals 0. So we start with tangent squared of x, and we add 3 to both sides. And then, this is tangent times tangent of x is equal to 3. So to remove the squared, the inverse function for squaring is to take the square root. When we introduce the square root, we also have to introduce a positive or negative, plus or minus square root of 3. So we now have the tangent of x is equal to a positive or negative square root of 3. And then we need to get to the x and the tangent's in the way. The inverse of tangent is the inverse tangent. If we take the inverse tangent of the left side, we have to take the inverse tangent of the right side. And x becomes whatever in our table of 9 for tangent is going to be our value, that is the square root of 3. So tangent of 30 is the square root of 3 over 3. It has all those 3's. The tangent of 45, sine over cosine, is a 1 here. And the tangent of 60 is plain old square root of 3. So we know that we have our solution when we're looking at pi over 3 radians. Pi over 3 is going to be here and here for the positives, but we also need the negatives, so we need these 2 values as well. So technically we could write 4 solutions, but I have a feeling that we can tighten this up a little bit. If we're looking at pi over 3, rather than talking about a full rotation around the unit circle, maybe we can just talk about these 2 together. How far apart are they on the unit circle? Well, they're pi radians apart. So if we say pi over 3 plus pi n, that will take care of pi over 3, and it will also take care of 4 pi over 3. Because if I add pi to pi over 3, 3 pi over 3 to pi over 3 becomes 4 pi over 3. Add another 3 pi over 3 to 4 pi over 3, we're at 7 pi over 3, so we end up getting to these 2 values over and over and over again. Likewise, we can do the same thing for our negatives. At 2 pi over 3, we have a solution. And because its other counterpart is directly opposite it on the unit circle, pi removed, we can call that plus pi n. All right, here's our next equation. And first instinct is to simply divide by the cosecant of x, because then we make things easier. However, it's possible, it won't be in this case, but it's possible that you'll lose solutions to your equation when you do that. Anytime you divide by a variable, you run the risk of losing solutions. So we want to gather everybody to one side. If we have the secant of x times the cosecant of x, and we subtract a cosecant of x from both sides, we get a 0. Now we notice that these two both have a cosecant in common, so if we take the greatest common factor out, we will have a secant of x when we divide by that cosecant of x, and we will have a negative 1 when we divide by the cosecant of x. So whenever we have something like x times x minus 5 equals 0, that means that we have two possible solutions. X could be equal to 0, or x minus 5 could be equal to 0. The same thing holds here. We're going to take the cosecant of x and let it be equal to 0. Or we can let the secant of x minus 1 be equal to 0. So in our first scenario, we want to know where is the cosecant of x equal to 0. If you're very familiar with the cosecant's graph, you can probably picture it and see what our answer to that piece is. But we also know that the cosecant is 1 over the sine of x, and that's supposed to be equal to 0. If we want to know what's actually happening here, if we find the reciprocal of each side, we would have the sine of x is equal to 1 over 0, and we ask ourselves, is the sine ever undefined? And that does not ever happen. Another way to look at that is to say, let's sketch our quick graph of sine of x. Sine of x starts at the origin, and it ends at 0 at 2 pi, starting and ending at the same place. At pi, in the middle, it's also at 0, but it raises at pi over 2 to 1, and is negative 1 at 3 pi over 2. And so we have our sine wave. We ask ourselves, is that ever undefined? Nope. And when we're thinking about what the cosecant looked like, I need to continue this on here. If we ask ourselves what the cosecant looked like, it was asymptotic anywhere the sine was 0, and had relative mins and maxes. This was its relative min heading up, relative max heading down. So we ask ourselves, is the cosecant ever going to get to be 0? And that is not possible. So there's no solution to the left side of our equation, or the left product factor of our equation. So the second part says, let's take the secant of x and let it be equal to 1. Secant is 1 over the cosine of x. And so we're asking ourselves next, where is the cosine of x going to be equal to 1? Well, if we just sketch a quick graph, we know that the cosine starts high, at its max amplitude, ends high. They always start and end at the same place, period of 2 pi. And it's low halfway in between. And the other pi over 2 and 3 pi over 2 are where it is 0. So where would the cosine be a positive 1? It would be a positive 1 at 0, at 2 pi, at 4 pi, at 6 pi, at 8 pi. So the cosine, or the x, so x would be equal to 0 if you want to hold that place, plus 2 pi n, or simply 2 pi n. Another way of looking at these, it would be to say, hey, where is the cosine on my unit circle equal to 1? We know that the cosine is always the x coordinate, So where do we have an x coordinate that's 1 on the unit circle? At 0, at 2 pi, at 4 pi, and so on. All right, here's another example. We've got the cosecant of 2x is equal to a positive 2 over the square root of 3 when we bring it to the other side. Instinctively, we want to rationalize that denominator, but let's ask ourselves, are we comfortable and familiar and well versed in cosecant? And chances are that answer is no. So the reciprocal of cosecant is going to be 1 over, or cosecant is 1 over the sine of 2x. And if we want to evaluate or get the sine into the numerator, it is as if we are inverting both sides, both fractions. So the sine of 2x is equal to the square root of 3 over 2. So if the sine of 2x is equal to the square root of 3 over 2, we need to get to that 2x, and we have a sine in the way. The inverse of sine is the inverse sine. So when we take the inverse sine of the sine of 2x, we get simply 2x. And when we take the inverse sine of the square root of 3 over 2 in our table of 3 for sine, our square root of 3 over 2 is the 60 degree or pi over 3 angle. So we know that we're working with a pi over 3. In our minimalist unit circle, the sine is positive in the first quadrant, and the sine is also positive in the second quadrant. So we need that pi over 3, and we need a 2 pi over 3. Let's talk about our rotations here. These are not pi removed from each other, 180 degrees removed from each other, so we have to list them both. So we would have a 2 pi n for both. And then we have to ask ourselves, what are we going to do with that 2? So we want the x all by itself. We're going to divide each term by 2, which is the same thing as multiplying by a half. And so our final solutions are x is equal to pi over 6 plus pi n, and also pi over 3 plus pi n. Now we ask ourselves, does that make sense? Well, what did the 2 in front of the x stand for? That was our variable b, and b impacted the period. It was 2 pi divided by b. So this is occurring twice as frequently as it would have before because of the 2 that is being multiplied by x. So it makes sense then that these would occur twice as frequently as they were before. And there's the assignment. So today we're going to be working with something similar. What we should notice though is that we have some new directions. Instead of finding all solutions, we're looking for the interval of 0 to 2 pi, inclusive of 0 but exclusive of 2 pi. So we're only interested in one rotation, one revolution around the unit circle, and because 0 is the same as 2 pi in terms of our answers for cosine, sine, and tangent, they only want you to include the solutions once, so they'll ask you to find only the solutions for 0 up to but not including 2 pi. So when we're solving these, it's very similar to what we did yesterday or in this previous one, but now in most cases the terms aren't factored already. So we have to ask ourselves mentally, could we take 2 x squared plus x minus 1 and factor that? And the answer, of course, is yes. It's going to be a binomial times a binomial. So we ask ourselves, what are the only ways that we can get 2 cosine squared of x? We can multiply 2 cosine of x times the cosine of x. 2 times 1, the only integer ways of multiplying to get 2. What are factors of 1? The only factors of 1 are 1 and 1, integer-wise. And so then what would we need to do with our signs? We need to have a negative 1, but we want our net result to be positive. So one of these signs needs to be negative, one needs to be positive, and we want the larger one to be the positive. So if we would put a negative here, we would have a negative 2 cosine of x and a positive 1 cosine of x, and that would give us a negative in the middle. So it's kind of a guess and check. We're going to try it this way. If we mentally FOIL this out now, a positive 2 cosine x times a positive 1 gets me 2 cosine x. A negative cosine x is added to it to give me a positive cosine x, and then a negative 1 times 1 is a negative 1. So we have our 2 factors. We set each of these factors equal to 0. And then we solve this. So we have to add 1 to both sides, divide by 2, and take the inverse cosine of both sides. So x is going to be whatever values, whatever angle measures make the cosine a positive 1/2. So we know that the cosine is a positive value in the first and the fourth quadrants, and it will be a positive 1/2 at pi over 3, and the pi over 3 in the fourth quadrant, which is 5 pi over 3. So x will be pi over 3 and 5 pi over 3 for the first 2 values. Now we say, where is the cosine of x going to be equal to a negative 1? So when we take the inverse cosine of the cosine of x, we're taking the inverse cosine of a negative 1. And x will be equal to, well, where in our unit circle is our cosine going to be a negative 1? In other words, where will it have a negative 1 for its coordinate? That will be pi, or 180 degrees. Because it said on the interval 0 to 2 pi, we only want to include these. We don't need the rotations to talk about the infinite number of solutions that would make that possible. In our next example, we have 2 cosine squared x plus 3 sine x minus 3 equals 0, again on the interval from 0 to pi over 2, exclusive of pi over 2. So the problem with this one is we have 2 trig functions. It's like asking you to factor 2y squared plus 3x minus 3. And we can't factor 2 different variables. So we ask ourselves, is there some way that we could make this look like this? So we recall that we have a Pythagorean identity that says that sine squared of theta plus cosine squared of theta is equal to 1. So if we want to talk about cosine squared in terms of sine squared, if we subtracted our sine squared of theta from both sides, cosine squared of theta is equal to 1 minus the sine squared of theta. So in place of this cosine squared of theta, we're going to plug in a 1 minus sine squared of theta. Or x in our case. Distributing, we get 2 minus 2 sine squared of x plus 3 sine of x minus 3 equals 0. We have like terms here, so let's write this in descending powers of sine. Negative 2 sine squared x plus 3 sine of x minus 1 equals 0. So now we're trying to factor negative 2x squared plus 3x minus 1. So again, there's only one way to get a negative 2x squared with a negative 1 as our other factor. So let's try a negative 2 sine of x times a 1 sine of x to get our negative 2. And we know that, again, we have to have one positive and one negative, but we want the bigger one to be positive. So if we take a 1 and 1 and place them there, and we multiply the negative 2 times a negative 1, that would give us a positive 2 sine of x, and then a positive 1 times the sine of x will give us a positive 3 sine of x, and our positive 1 times our negative 1 becomes negative 1. So what makes this first parentheses equal to 0? If we bring our 1 to the other side, it will be negative. Dividing by negative 2, sine of x will be a positive 1/2. What makes our second parentheses equal to 0? If we bring the 1 to the other side, we're adding 1 to both sides, and sine of x is equal to a positive 1. So we ask ourselves, where is the sine of x in our table of 9 going to be equal to a 1/2? And that would be a pi over 6, a 30-degree angle in the first quadrant, and also a positive 1/2 in the second quadrant for sine. And so we will have a pi over 6 and a 5 pi over 6. And then we ask ourselves, where is the sine of x equal to a positive 1? In our ordered pairs, it's cosine, sine, and the y-coordinate is the sine. So we ask on the unit circle, where would the sine be a positive 1? And that's going to be up here at the ordered pair 1, 0, 1. And so that would be a pi over 2. Or if you prefer, sketch a quick sine wave. Sine starts in the middle, ends in the middle, and the middle's in the middle, and it's high and low. And so at pi over 2 is where it's going to be positive 1. So those are our solutions on the interval of 0 to 2 pi. Next, we're solving sine secant of x plus 1 equals tangent of x on this interval. Once again, we have two separate trig functions, two different trig functions, but we don't have the advantage of them being squared. We know that the tangent squared of x plus 1 is equal to the secant squared of x from our Pythagorean identities. So if we square both sides of the equation, we can do that, and we will end up with a tangent squared of x, which could be utilized to help us get this in terms of just one trig function. We have to remember, though, that when we're taking the secant of x plus 1 and we're squaring it, that's taking the secant of x plus 1 times itself. So we square the first, multiply them together and double them, and square the last. Now let's do a substitution. If the secant squared of x plus 2 secant of x plus 1 is equal to the tangent squared of x, the tangent squared of x will be equal to the secant squared of x minus 1. Combining like terms, if we subtract a secant squared of x from both sides, our secant squareds are eliminated. So let's move the 1 to the right side and have 2 secant of x is equal to a negative 2. Dividing by 2, secant of x is equal to a negative 1. So the secant is the 1 over the cosine of x. We're wanting to know, where is the cosine of x? A negative 1, which ordered pair would give us a negative 1 for x. And we're negative 1, 0 here at pi. So our solution is going to be pi. Lastly, we need to find all solutions of 6 times the cosine squared of x minus 11 cosine of x minus is equal to a negative 5. So we'll start by gathering everybody on one side. And then asking ourselves, could we factor 6x squared minus 11x plus 5? And most of these are going to be easily factorable. We know 6 plus 5 gets us 11, so let's start by 6 cosine squared of x and cosine of x. Of course, you could multiply the two, 6 and 5 together, and ask yourself what are factors of 30. That will add to become a negative 11 and work it out that way with grouping, by factoring by grouping, but these will usually be a much simpler type of problem. So if we're trying to put 5 and 1 somewhere, if we put the 5 here, we would end up with 30, so we need 5 in this spot and 1 here. They both have to be positive or negative because we have a positive 5, and this sign tells us they both have to be negative. So if 6 times the cosine squared of x minus 5 is equal to 0, that means 6 times the cosine squared of x is equal to a positive 5, and the cosine squared of x is a positive 5/6. So we take the, heavens, where did I get my cosine squared? Apologies. These should all be the first power. All right, so we take the cosine of x and we ask ourselves, do we recognize this value as one of our table of 9? And we say absolutely not. So we are going to have to take the inverse cosine of the cosine of x and the inverse cosine of 5/6. We have been talking about everything in terms of radians, so make sure your calculator is in radian mode. And evaluate. Let's talk about the other side first. Cosine of x is equal to a positive 1. So we ask ourselves which values will give us a positive 1 for cosine of x. And that happens here at 0 degrees, 0 radians. And this time we want all solutions. So we would say x equals 0 plus 2 pi n. And now let's go evaluate that calculator in radian mode. I don't know if I have a calculator that will do that for me. But when we find our solution, it's like 0.568 or something like that radians. So it will be here in this first quadrant, but also down here in the fourth quadrant. And so when you do that, it doesn't matter to me if you take a shortcut and say whatever that radian measure is plus 2 pi n from up here, and then also a negative whatever that is plus 2 pi n. So inverse cosine of 5/6. Let's go break out some calculator. So 0.586 is our solution, or our answer. And it would also be in the fourth quadrant, so a negative 0.586. Or you could take 2 pi minus that 0.586. And work it out from there. And there's your assignment.